SciCuriousID presents. If there is one conclusion that cannot be avoided, it is this: there is no simple way out of the energy dilemma. In the previous episodes, we have seen the limits of affordability, the demands of security, and the cost of sustainability. We have seen how trade-offs are not political choices, but physical ones. By episode 5, one reality became clear: no single solution satisfies all constraints. And yet, policy debates, public narratives, and long-term plans often behave as if complexity itself could be negotiated away. But energy systems do not respond to slogans. They respond to physics. They respond to materials. They respond to time. Modern civilization depends on continuous, high-density energy flows. Not occasionally, not symbolically, but every second without interruption. Ignoring these constraints does not make them disappear. It merely shifts the risk, from planning tables to power grids, from forecasts to failures. This episode is not about what we wish energy systems could be. It is about what they are, and the consequences of pretending otherwise. Because the most dangerous illusion in an energy transition is not delay, it is denial.
Behind every question lies discovery. I'm Saluna, and this is SciCurious, where we uncover the science shaping our world.
The global energy transition is often described as a simple substitution. Replace fossil fuels with renewable energy. Lower emissions. Move forward. But beneath this elegant narrative lies a paradox rarely discussed. To build a green energy system, we must first extract and process enormous quantities of minerals. And to produce those minerals, we still rely overwhelmingly on fossil energy. This is the chicken and egg problem of the energy transition. Modern renewable energy systems are not fuel-intensive, they are material-intensive. Electrification requires vast quantities of copper for cables, motors, and transformers. Nickel, cobalt, and lithium for batteries. Aluminium, steel, and rare earth elements for turbines and grids. Multiple international studies show that a fully electrified energy system requires 2 to 4 times more critical minerals than a conventional fossil-based system. Clean energy does not remove resource dependence. It shifts it. Mining is only the first step in the energy transition supply chain. Raw ore has little value on its own. The real transformation happens downstream, in refining and smelting. This is where energy demand accelerates dramatically. For many critical minerals, more than half of total life cycle energy use occurs after the mine. Smelting is among the most energy-intensive industrial processes on Earth. Nickel processing provides a clear example. Depending on technology, producing 1 ton of refined nickel can require 13 to 15,000 kilowatt-hours of electricity. This energy must be continuous, stable, affordable. Today, almost everywhere in the world, such power still comes primarily from coal and gas. There is no scalable alternative yet. As advanced economies decarbonize their electricity systems, a new pattern has emerged. Energy-intensive industries relocate. Smelting, refining, and heavy manufacturing move to regions with cheaper, more reliable fossil power. The result is carbon leakage. Emissions are not eliminated, but displaced. From a global climate perspective, this creates the illusion of progress without equivalent reductions. This material shift is reshaping global geopolitics. For the last century, energy security was defined by access to oil, centered largely on the Middle East. Today, security depends on control over critical minerals. China, for example, controls roughly 60% of the world's lithium processing and nearly 80% of cobalt refining. The West has outsourced these dirty industries for decades. Now, as they rush to reindustrialize, they face a stark reality. Building new supply chains is far harder than disrupting old ones. We are trading dependence on OPEC for dependence on a new, more fragmented mineral order. Optimists point to recycling as the escape route. But the timeline of physics rarely matches the timeline of politics. Recycling cannot solve the supply crunch today. With EV adoption growing exponentially, most batteries are brand new. They will not reach end of life for another 15 years. We cannot recycle batteries that are currently on the road. Similarly, green mining technologies exist primarily in pilot projects. They are not yet ready to replace the massive diesel and coal backbone of the global mining industry at the scale required. Every successful energy transition in history has followed a sequence. First comes abundant primary energy, then infrastructure and industry. Only then does large-scale system transformation occur. Attempting to reverse this order increases costs, fragility, and dependence on imports. This is not a failure of ambition. It is a constraint of physics and engineering. Indonesia sits at the center of this paradox. The country is essential to the global mineral supply chain for clean energy. Yet building that supply chain depends, today, on reliable domestic fossil power. Recognizing this reality does not delay transition. It makes it possible. The real question is not whether coal is good or bad. The real question is whether we are willing to take responsibility for the system we actually use. Energy transitions do not happen through slogans. They happen through materials, infrastructure, capital, and time. Ignoring physical constraints does not make them disappear. Ignoring industrial demand does not reduce it. Responsibility means planning honestly, acknowledging trade-offs, costs, and limits, without ideology, without denial. Coal is not an idea. It is a system reality. And responsible transitions begin not with promises, but with facts we are willing to face. What comes next is not a solution, but a choice.
There's always more to discover. I'm Selu, and this has been SciCurious. Stay curious, and I'll see you in the next wonder.